Hi guys, welcome to this set of videos. What we're going to do here is these videos are going to follow along with the notes that come out of your textbook from Chapter 4, Section 7. And what we're going to do here in this set of videos or in this section is we're actually going to go back to something that we did in Chapter 2 that I told you was going to continue to come back in essentially every chapter we're going to do here in Algebra 2. So hopefully you'll recall back in Chapter 2, Section 7, we looked at transformations of parent functions. And I told you guys when we did that section, Chapter 2, Section 7, that you wanted to pay close attention and make sure you really understood that section, Chapter 2, Section 7, because it was going to continue to come back. Here it is. So Chapter 4, Section 7, we are going to go all the way back to Chapter 2, Section 7 and just sort of review what you guys learned in that section about the transformations, right? Transformations of quadratic functions. What that means is that this section is a review of what we did back in Chapter 2. And if you're not familiar with transformations or you think you may have forgotten what we did, just go back to Chapter 2, re-watch those videos from Section 7 to kind of refresh your memory. I am going to go through this note set and these videos with the assumption that you remember everything we talked about back in Chapter 2, Section 7. So with that in mind, what we're going to do is we're going to analyze the graphs of quadratic functions. So we started Chapter 4 by looking at the graphs of quadratics, and now we're going to finish Chapter 4 by looking at graphs of quadratics. And you've got two objectives or learning targets here in this set of notes. What you should be able to do by the time we get to the end of these videos. You should be able to write a quadratic function in vertex form. And the vertex form you should recognize again from Chapter 2, Section 7 is y equals a times the quantity x minus h squared plus k, where a, h, and k represent your transformations. And then your second one, transform the graphs of quadratic functions again using that vertex form. By figuring out or by knowing what your a, your h, and your k are, you should be able to transform the parent function, which for quadratics, you'll remember, sorry, not highlighter, you'll remember is y equals x squared, right? So this is the parent function for quadratics, and what we do to the parent function is we transform it by shifting it up or down, moving it left or right, by doing dilations or reflections, and that's what a, h, and k do to the parent function. So let's just go ahead and jump right into these, and here's where we're going to start. I just real quick want to go over with you why we've kind of taken a break. What we did, like I said, we started the chapter by looking at graphs of quadratics. Then we kind of in the middle sections, essentially starting in Section 3, is we looked at factoring, right? And the perfect form, right, this standard form for a quadratic, this guy right here, works well when you're looking for solutions or trying to solve a quadratic, right? Given to you in standard form, it can be factored, right? You can use GCF, difference of squares, perfect square trinomial, general trinomials, complete the square, quadratic formula, whatever. All of those different methods work great when your quadratic is in standard form, and factoring allows you to find the roots or the solutions for this particular quadratic. But now we're going back to graphing in this section, and unfortunately, standard form for a quadratic really doesn't do me a whole lot of good when it comes to graphing. It just doesn't tell me very much. It's kind of useless. And so instead, what we'll use is that form that we learned back in Chapter 2, Section 7, which is the vertex form. So again, like I said, you should remember this, and if you don't remember this from Chapter 2, Section 7, just jump back to that section and quickly kind of refresh your memory on it. I am going to move forward like you remember what we did back in Chapter 2, Section 7. And this form presents the necessary information for graphing in an easy-to-read format. So unlike standard form, having your quadratic in vertex form actually makes graphing the function very, very easy. Once you know a, h, and k, you just simply perform the transformations to the parent function, and you've got your graph. I just run through here quickly with you, again, what each of those transformations mean, what k and h and a will do to the parent function. Of course, the vertex is going to be at hk. The axis of symmetry is at x equals h. Quick note, remember that h is the opposite, right? So in my vertex form, if h is positive, you would actually shift your graph in the horizontally in the negative direction. If h was a negative number, you would shift your graph horizontally in the positive direction. So just remember that about h. So what we're going to do here in the next couple of problems here on the next page of the notes is we're going to look at how do you go from standard form, which doesn't really tell me much about the graph of a function, to vertex form, which tells me everything I need to know about the graph of the quadratic function. So how do you go from standard form to vertex form? That's what we're going to look at. And before we take a look at a couple of example problems, let me go over with you just real quickly here how it works. So what we're going to do in order to go from standard form to vertex form is we're going to complete the square. But this completing the square, which we did here in this chapter in section 5, we have a whole note set and videos on completing the square. Let me refresh with you kind of how that method worked. What you were given in order to complete the square was you were given a quadratic in standard form. It looked like this: ax squared plus bx plus c is equal to 0. And of course what we did is, well, what we're going to do is we're going to assume that this leading coefficient is a 1. Now remember, if a is not a 1, we just simply divide everybody by a and force that leading coefficient to be a 1. But I'm not going to do that here. We'll just assume that a is a 1, and what I've actually got is x squared plus bx plus c is equal to 0. And so now I've got my leading coefficient of 1, which is what I need to have in order to complete the square. Now the way that completing the square worked was we take whatever this constant value is and we just moved it to the other side to make space for my b squared over 4. So I had x squared plus bx is equal to a negative c. And now in order to complete the square, we added b squared over 4 to both sides of the equation, because algebra says whatever you do to one side, you have to do to both sides. So we had x squared plus bx, and then we would add b squared over 4. Well, what this did is it gives me a perfect square trinomial on what for you guys is the left-hand side of the equal sign. And so we factored it as a perfect square trinomial. Which was going to be x and x. This guy's a plus sign, so it means both of my numbers have to be positive. And because this is a perfect square, the numbers have to be the same number. It would be a b over 2 and a b over 2. Well, since these binomials are the same, I can rewrite them as x plus b over 2 squared is all equal to negative c plus b squared over 4. And hopefully you guys remember from there what we would do is just use the square root property where you take the square root of both sides and solve for x from there. So that was completing the square, which we looked at in section 5 of this chapter. But what we're going to do today is going to be slightly different, and here's the reason why. When we did these problems, completing the square in section 5, I had a quadratic equation that was set equal to 0. Why was it set equal to 0? Well, because I was looking for the roots, right? I'm looking for x-intercepts. And when you cross the x-axis, y is equal to 0. Right, so I had my quadratic set equal to 0, and because I had a 0 over here, I just worked on both sides of the equal sign. What we're going to run into today is you will not have a 0 on the other side of the equal sign. Actually, what you're going to have is a function. And remember, the function is going to be f of x equals, s of x equals, q of s equals. You can name the function whatever you want to, or it might just be y. Y equals ax squared plus bx plus c. And here's where we're going to run into our issue. In order to graph a function, it has to be in the form y equals. Right? I can't take this c and move it over to the other side because I have to leave my function y equals, not y minus c equals. Right? It doesn't work that way. It's a function. It has to be y equals some expression in terms of x. So what that means is today we're going to complete the square, but instead of being able to work on both sides of the equal sign like we did in section 5, what we're going to do today is we're going to complete the square, and I have to be able to do that all on the same side of the equal sign so that I always have a y equals on the left-hand side. Here's how we're going to do it. Again, we're going to assume that a is a leading coefficient of 1. I'll show you later on what to do if it isn't. We can certainly deal with it, but let's just for now assume that it is. And so I have y equals x squared plus bx plus c. What we're going to do is we're going to use parentheses to kind of break up the right-hand side of this equation. Y equals, we're going to put our terms, our quadratic and our linear term, inside parentheses. Now, here's the way that equations work, right? What I did, the way algebra works is over here, this guy, right? I've got this equation, and I added a b squared over 4 on one side. It's sort of like you have this balance, right? Think of it as scales, your equation as a scale, and I added a b squared over 4 on one side. Well, algebra says that they have to be equal, right? That's what the equal sign means. And I added a b squared over 4 on one side, so I just simply add b squared over 4 on the other side, and I maintain my equality. That's why I add b squared over 4 on both sides. Well, what we're going to do here is I have an x squared plus bx, and I want this to be a perfect square trinomial. So inside the parentheses, I'm going to add a b squared over 4. So let's do that. Y equals x squared plus bx plus b squared over 4. But now here's my problem, right? In order to, because I've added something, right? I added something to one side, I now no longer have equality. To fix that, I just simply added the same amount to the other side of the equation, and it came back into balance. But I can't do that here because this has to stay y equals. I can't just simply add b squared over 4 to the other side because then I wouldn't have y equals. I'd have y plus b squared over 4 equals, and I don't want that. I need it to stay y equals. So what we're going to do is instead of adding b squared over 4 to the other side, I've added b squared over 4 to one side inside the parentheses. Outside the parentheses, I'll just subtract b squared over 4. And that'll fix my equality. So now what I've got is plus c minus b squared over 4. And I know that I have maintained equality, and here's the reason why. If I were to combine like terms, a positive b squared over 4 minus b squared over 4 cancels each other out, and I get right back to what I originally had. So I have completed the square, but maintained equality at the same time, and I did it using parentheses. Add b squared over 4 inside the parentheses. This is now a perfect square trinomial. And to balance out the equation, subtract b squared over 4 outside of the parentheses. And so now what I have is y equals x plus b over 2 times x plus b over 2 plus c minus b squared over 4, which is y equals x plus b over 2 squared plus c minus b squared over 4. It is still completing the square. It's just going to look a little different in this section because I'm not able to work on both sides of the equal sign. I have to do all my work on one side so that it stays y equals the whole way through the problem. And that's what we're going to do on the next page of the notes. So head on over and I'll meet you guys there.